Good morning, everyone. Today, I want to introduce my recent work in WashU about thermal precipitate design. My presentation mainly contains 4 parts. The first is the motivation and object. Now let's begin with my motivation. Before introducing my motivation, I want to ask a question. Do you know which is the most contributor to the air pollution?
Emission of autos.
Okay. Are there any other questions? Okay. The particular measure pollution has become the most contributor to the air pollution. In the last presentation, you may remember I have introduced the detailed information about the lung structure. And now I want to investigate the particle toxicity to our lung system. And nowadays, there's many researchers using animals to study this question. And for me, I prefer in vitro method. So I want to get some cells from the lung surface, or from human or from animals. Look at this picture. This is the white used A549 cell line. I culture the cells to form a monolayer. Then I can make some particles deposit on the surface. In this way, we can investigate the cell response. Okay. Now I want to introduce the traditional exposure model. This is the epithelium cell monolayer, and this is the surface environment. And the cells are cultured in the cell culture medium. This is the liquid exposure environment. In this model, large particles can deposit quickly, but the deposit velocity decreases with the particle diameter decreasing. Okay, for small particles, their deposit path will be greatly affected by the Brown motion, especially for small particles. For ultrafine particles with a diameter less than 100 nanometer, so it becomes not so easy for them to deposit on the surface. So this will affect the corresponding cell response. So what I want to do, I want to develop a new model in the air environment. Look at this. I want to culture the cells in the air environment, and make the particles with the different diameters can deposit at the same time, like this way. So through my problem, I have found out some method, and now I introduce one method. This is called thermophoresis. Have you ever learned something or heard something about thermophoresis?
We did about the warmer object will flow upward,
Yeah.
colder will.
Yeah, correct. Yeah. And now I want to use this animation to explain this phenomenon. It's very interesting. Okay, suppose this is the smoke current, and this is the smoke particles, and we immerse a heated metal rod with high temperature in the smoke. So from this animation, what have you observed? Okay. Very simple. The particles are repelled from the heated rod. And there's another interesting thing. Is there is a particle layer. But what is the particle layer? Particle layer means the particles can't attach the heated rod because because some force will repel the particles. Do you know why there is a particle layer?
Because of the heat?
Yeah. Why the heat can help to form the particle layer?
Because there is a velocity near the surface. Air is coming out from the sphere, right?
Is it because the heat in the air makes the atoms velocity higher, and they can move faster, so they can
Yeah,
attach?
it makes sense. Okay. Okay. I want to use another animation to explain this phenomenon. Yes, you're right. Yeah. Suppose this is a hard site, and this is a cool site, and this two is the air molecules, and this is the blue one is the air molecule from the cool site, and this one from the hot site, and there's a particle entering in this direction. Yeah. The air molecules from the hot site have great momentum, and the molecule from the cool site have less momentum. So this will form a net force pushing the particles in the cool direction. Yeah, you got it? Okay. In 1980, Talbot proposed a formula to describe this phenomena and to give the thermophoretic velocity. From this formula, it is very easy to find the VTH positively correlate with the temperature gradient, and the negative correlate with the temperature of the particle, and also have a relationship